Uh, Good afternoon, everybody, and welcome to this ICTS Distinguished Lecture, in which we are very fortunate to have Professor Giorgio Parisi, winner of the Nobel Prize in this year, to address us. My name is Chandan Dasgupta. I will be conducting this session. First thing that we'd like to do is to request Professor Rajesh Gopakumar, Director of ICTS, to say a few things about ICTS.
Thank you very much, Chandan. And as Chandan mentioned, welcome to this special ICTS Distinguished Lecture given by none other than Professor Giorgio Parisi. Before, I know all of you are waiting to hear him, but before that, I will do a small little presentation to, since you couldn't be here at ICTS, all of you in the audience couldn't be here at ICTS for this lecture in person, which is what we would normally have had in better times. This is in lieu of that. So ICTS is a very new institute. It's one of the newest centers of the Tata Institute of Fundamental Research. And it is patterned on several peer institutions elsewhere in the world, like the KITP in Santa Barbara, the MSRI for Mathematics at Berkeley, the Simon Center, the GGI, IAS Princeton, and so on, but with innovations especially tailored for the Indian context. And what the unique mandate of this center of TIFR is to not only have in-house research, about which I'll say a little bit, but the important ingredient is that we have these high-quality visitor programs, like many of these institutions mentioned here. And these visitor programs are not just in physics, they are actually spanning physics, mathematics, computer science, quantitative biology, and recently in climate sciences even, which is of course the theme of one of the themes of this year's Nobel Prize. But so these are intertwined in a certain sense, and together with that, we also do a disproportionate amount of outreach and engaging with the broader society on science. I won't have time to sort of go into depth in any of them, but just as I promised to give you a few snapshots. By the way, this is one of the iconic buildings of the ICTS campus, our library, and this is one of the participants of our program had drawn a beautiful watercolor of that, which he then presented to us. So this was the watercolor that I mentioned. This was, of course, the intertwined nature of our mandate between the in-house research, the programs, and the outreach, and the programs in a number of disciplines. And the library that I was mentioning, and the watercolor. So a little about our research. We have faculty who are high quality researchers with very strong core strengths, but we do not have departments. We do not have any kind of real compartments. So we expect our faculty to have interests across disciplines. And at the moment, we have a growing number of faculty, about nearly 30, as you can see. And these are the sort of full-time faculty at ICTS. And together with a active and growing PhD program and a postdoctoral program and so on. As I said, we don't have departments. We have somewhat fluid groupings, if you wish, and these are somewhat notional. And some of the areas are mentioned here more in the mathematical sciences are dynamical systems, PDEs, and someone who is going to join us next month in the climate sciences, or actually more precisely ocean sciences. And then we have geometry and mathematical physics, we have probability theory, and we actually will be expanding into theoretical computer science next year with a senior person joining. And in the more physical sciences, we have a very active group in astrophysics and relativity, general relativity, in particular, a group that's very highly involved with the LIGO in the LIGO collaboration and made important contributions to the LIGO discovery. Complex systems is, of course, nowadays a very an umbrella term, and we have people, this term here at ICTS comprises of people working in fluid dynamics, condensed matter physics, statistical physics, quantitative biology. And so it's a very large set of people, but again, that's a highly interactive group with people collaborating across these disciplines, and this is why, in a sense, they are sort of put together. And then we have a string theory and quantum field theory group, which includes myself and Spenta and others. So this is the snapshot of our current research profile and some of the faculty, as you can see. So but let me come to programs, which is where I'd like to sort of emphasize the role that ICTS plays. We have programs throughout the year, and Bangalore is blessed with a very moderate weather, even in these changing times. And we have a twice-a-year call for the global scientific community, just like many of the other institutions I mentioned at the beginning. So it's an open program proposal. It's vetted by a broad committee of experts. And there are two calls. There is one which is concluding this year, at the end of this year, December 31st. So there's still time to put in a proposal. And these are typically for programs that you would be organizing in the next year and a half. So so currently the call is open for programs until 2023 September, and then it will be for the next 6 months after that will be the call that ends in June, etc. Typically, our programs are 2 to 3 weeks long, and they have often a very strong pedagogical component, but to get younger researchers, especially across Indian institutions, exposed to some of the frontier areas, and we get global experts to participate in these programs. We have more intense collaborative discussion meetings, which are typically less than 2 weeks. In pre-pandemic times, we were organizing something like 25 events per year. It's a very packed schedule. We get many more proposals than we can actually host on campus. But once a program is supported, we support the program completely with both the material resources and the monetary resources, as well as the human resources in terms of the program organizations and so on. And we had something like 2,000 participants come through with a very large international component in the last year when we had programs in a normal way, which was 2019. Since 2020, things have been, of course, online, and we've had large number of participants, but in the online format. We archive all our talks, and this YouTube channel, ICTS Talks, is very popular. It is a permanent repository. It has now a huge number of very high quality lectures by top experts, and it's increasingly being watched by young researchers, people interested in science and so on. Just a collage of various programs we've had. Finally, let me just come to the ICTS Distinguished Lecture Series, which we are gathered here for today as part of the discussion meeting on the work of Giorgio Parisi. The ICTS Distinguished Lectures actually began about 10 years ago, and the first lecture was given by Ashok Sen, who was then at HRI, but has recently moved to ICTS. The second lecture, I believe, was given by Manjul Bhargava, the mathematician, and we've had a stream of great lectures in this series: Pierre Hohenberg, Nalini Anantraman on quantum chaos, David Gross, Alessandra Buonanno, Jennifer Chase, Duncan Haldane, and very recently Joel Lebowitz, and before that Susan Coppersmith, and many more. I mean, this is not an exhaustive list, but to give you a sense of the topics and the eminent scientists we have gathered at ICTS to have these lectures, and it's of course a pity that we are doing this online in some sense, but nevertheless, I think it makes it easier for Professor Parisi to join us today and give a talk on which we are all looking forward to. But I hope to see all of you in ICTS in person, hopefully in 2022 and beyond, at one of our events. So thank you very much.
Okay, thanks a lot, Rajesh, for this very nice introduction to activities of ICTS. Now I request Professor Smarajit Karmakar to introduce our distinguished speaker today.
Hi, Giorgio. Yeah, so it's indeed, thanks, Chandan, for giving me this opportunity to introduce Giorgio, and whom I admire a lot. And it's really a pleasure for me to introduce him. And it's really a happy moment that Giorgio won the Nobel Prize this year. And congratulations, Giorgio, once more. And I want to say that this is also a special moment for me because he's my former postdoc mentor, and my interaction with him when I was in Rome is something which I cherish. And I hope to continue that in the near future as well. Giorgio does not need any introduction, and he is one of the pioneers in the field, and he has worked in, he's probably one of the most versatile scientists who are amongst us. And just to name few, so he has worked starting from subatomic particles, then went on to study animal migratory behavior, climate science, computer science, and the list actually is very, very large. I'm not going to embarrass Giorgio by giving the full list, but for my other colleagues in the audience, I cannot stop without telling some of the prizes that he has won. And I think the list is also equally bigger on that front. So just to name a few, he has been given Boltzmann Medal, Dirac Medal, Enrico Fermi Prize, Lagrange Prize, Maxwell Medal, Lars Onsager Prize, Wolf Prize, and Microsoft Prize as well, and then finally the Nobel Prize. And this prize and awards acknowledges clearly the vast contribution Giorgio made in the field of complex systems. And apart from being a scientist, he is also an inspirational person for many of us. And I'm sure all of you are going to enjoy his lecture and interacting with him. And we have a significant amount of time. So I hope we'll have a very fruitful discussion with Giorgio in a few minutes. Okay, so over to you, Chandan, and I request Giorgio to give his lecture.
Okay, thank you, Smarajit. Just before Professor Parisi starts his lecture, I just wanted to mention one or two things about this Zoom protocol. Since we have a large audience, already see more than 200 people attending this session, we will turn off the mics during Professor Parisi's talk. So if you want to ask questions, then you can use this chat facility to basically write it down, and maybe at the end of the talk, we can come back to these questions. Same thing applies to people who are watching on YouTube. There again, there is a chat facility. So if you have questions, then please write them down, and after the talk, then we'll get to them. And after the talk also, you can raise your hand. There's a raised hand symbol in Zoom. So after the talk, if you have questions, then you can also use that. And then we'll again come to you and unmute your mic so that you can ask the question.
Q&A. Chat should be posted in Q&A.
The chat, if you're posting, then please post it to Q&A. Okay, so now we'll request Professor Parisi to start his lecture. Can you please share your screen, Professor Parisi?
Yes. Okay. So okay. 1 second that
Okay, I think you see the screen.
Yes.
Yes, we can, yeah.
Okay, so thank you very much for organizing this wonderful conference with so many people, so many friends speaking. And it was a great honor to have this conference that was dedicated to me. A wonderful, also congratulations for the wonderful graphics. And now I was not sure what I should speak about. And what I try to do something that is somewhat an essay, a tentative, and to try to understand why I've done, why I've done some papers and why and which were the tools that I had to do the things that I've done. Now, 1 second. Sorry. Okay. Now, the things that that sometimes have done some very fast intrusion in other people's field. For example, stochastic resonance and multi-fraternal turbulence. It's clear that the driving force was curiosity, but what I would like to try to find some logic in a trajectory. So one thing that is very important is the toolbox. I mean, the point is the following, that doing some work in a given field, you acquire some knowledge and you learn some technique. Feynman was stressing in some places the importance of toolbox. So I will try to understand where the things come from, where I learned the techniques that I used before, and at the beginning, I will stress the new things that I learned during some paper, and later I will try to put papers together with similar subject. Of course, it's clear that the things is I have to done a complete arbitrary selection of material. Also because I think that I've written the order 900 the paper, and 900 paper in 1 hour means 4 seconds per paper. So it's clear that some selection has to be done. Okay, so let me start from my first paper. My two first papers were done with Massimo Testa, and they were one was about generating functional word identity scalar mesons, and the second was about gauge invariance and dynamical symmetry breaking. These two papers have been very important for me because I learned a lot of the technique that I was using, that I used after. There was functional integral. There was a problem understanding symmetries of functional integral, or generating functionals, generating function for the connected, generating function from the disconnected, generating function for the vertices. So I have to understand all type of functional Lagrange transform and how to write word identities as invariance of the functionals with local group rotation and the role of functional level of the network currents. And this was done in problem of the first paper was a problem of some phenomenological model for scalar meson that were about SU3 cross SU3. And the thing that was interesting also was that I have to learn all the technique about symmetry, spontaneous symmetry breaking from one side, and that was very useful for me later on. I have to tell, generally speaking, that I have a very strong interest for mathematics, and I remember that there were many of these subjects which I studied also carefully from the mathematical viewpoint. Later on, I started to work on with Khabib, my mentor, and with Khabib and Verganelakis on hadron production in a plus and minus collision and deep inelastic scattering. And now these two papers have been important because I learned, I started to reflect on many different things. For example, the asymptotic behavior in field theory. Also was important, something that has been completely forgotten, but was very useful, especially at the time, was a perturbation theory at infinite momentum frame. Of course, normally you use covariant perturbation theory, but for certain aims, it's useful to do non-covariant perturbation theory, which is usually considered to be MS, in infinite momentum frame. And the other two papers of that period were papers that were done with Francesco Zirilli, that was essentially connected to the fact that I was in Frascati, and I was in Frascati, people were doing a plus and minus collisions, and there were some methods, essentially Watzeke-Williams, or modified Watzeke-Williams, to compute processes in electrodynamics. And this is something that also has been quite useful in later stage, So this was my starting point. I graduated in 70, and so this was something that I was doing just after graduation. Now, in 71, I started to be interested by phase transitions. That was that the reason was clear. We had in a room Iona Lasigno and Carlo De Castro that were doing study of phase transition using the renormalization group. The renormalization group is a technique that is I studied on quantum field theory textbook, and also my good friend Adero and Pelliti were doing some thesis with Iona and De Castro Iona. And so I started to be interested in the field, and we noticed a paper of Polyakov in the end of the 70s or beginning of 71. At the time, we were reading the Soviet physics papers translated, and on conformal bootstrap. There was some idea to use conformal symmetry. And we did the first paper with Deramo, Parisi, and Pelliti on theoretical prediction for critical exponent. However, what it turns out, semantics showed me that the paper was wrong. I mean, we did a conceptual error. At certain moment in the computation, there was a 0 divided 0. So we did not pay attention to the fact there was 0 divided 0, and we simplified the 0. And you see that when you do this type of things, you get something that is nonsense. And the other paper with Pelliti was correct, but and this was very interesting for me, these two papers, because I started to be interested both to scaling not in quantum field theory, but scaling in statistical mechanics, the former interest in statistical mechanics, and conformal invariant field theory. Now, I was fortunate that I was in Frascati. In Frascati, there was also Ferrara Grillo that was working with Raul Gatto. Gatto at that moment came to Rome. And I was interested to conformal group in order to compute critical exponent. And they were interested in the general thing for the conformal group. And they think that we started a new bootstrap program, a bootstrap program that is the one that is realized now by all the paper by Slava Rykov and also the collaboration. And we essentially start to write the formalism for constructing the 4-point function in terms of conformal building block. And that was something that for the moment it was not useful. It started to be useful, let's say 45 years later, but it was not, but it was something that for me was very useful because I started to be very familiar with all type of techniques to compute integral. The integral that we had to compute were very complex. Of course, we were using the Grasstein book for doing integral. It was before Mathematica. And I had to become very familiar with all the panoplia of techniques that were used to do in this type of integral: Fourier Laplace transform, Fourier transform, Laplace transform, complex integral, contour deformation, all this type of problems. A completely different interest that I had at that time, because I had some good friends, especially Giovanni Lucano and Gianluca Romano, and also Sandro Pace. They were doing experiment of aluminum film, and I was interested in two-dimensional behavior. Now, two-dimensional behavior for superconductivity is something that was quite interesting. This was before Kosteles and Thouless. So I did one experimental work with them, and I did also two theoretical work. One had the aim of understanding their data, and the other thing that was like to try to understand the fact how could you have a persistent current in two-dimensional superconductor, where I knew that from Goldstone's theorem and that there were some problems. And this was interesting for me because I have to learn nonlinear equation in field theory, and also non-perturbative field theory tunnel effect. And that was important because it was not used, this technique were not used in that paper, but I had to study the paper by Lange, in which he was discussing all this type of dynamical problem of tunneling, of metastability of current, how current could decay in one-dimensional system, how they could decay in two-dimensional system, and so on. And and also the thing that was interesting, that I had to confront myself with dynamical phenomena, and there's all the problem to understand how you write a dynamical phenomena in nonlinear, in quantum, in statistical field theory. Therefore, all Langevin equation, the Langevin equation approach, I started to be familiar with Langevin equation and things like that at that particular moment. Well, in that more or less in that period, I started to be very interested to the critical exponent. As I told you, there was a work that I did with Pellitti and Deramo. And when people back then and in Hussein were so kind to invite me to give Cargese Lectures in '73, the book will remain unpublished, therefore my lectures appeared slightly modified in 7 years later. And that I started to understand in a deep way Wilson renormalization group, essentially also the four-minus-epsilon expansion. What I did was a computation also, well, a step forward. I made some framework to do the computation directly in 3 dimensions without having to resort to the Wilson expansion. And that was based on Callan-Simancic equations. And therefore, there was a lot of work on phase transition, critical exponent, and also loop computation, because something that I found very remarkable that I did in this case, a 3-loop computation of the critical exponent in 2 dimensions, in 3 dimensions. And it turned out that I did all computation without mistake. The result were correct, but I have to learn all the techniques to do this type of computation. Of course, I was very curious also on many other problems on field theory, non-perturbative effect. And one thing that was very interesting, it was non-renormalizable field theory. It was not completely clear if at the time, if weak interaction were renormalizable or not. It could be possible, it could be explored, the possibility of being non-renormalizable. And also gravity was, at that time, was non-renormalizable, so I was certainly interested in non-renormalizable stuff, and therefore I wrote 2 papers, and that was very interesting because I learned how to deal with a non-perturbative effect and all these techniques of integral representation that I was saying before were very important in this particular case. And the other things that I started in, was that period was in 73, was to try to understand in the framework of field theory what was happening depending on scattering. Now, from at that time was before asymptotic freedom. It was before asymptotic freedom, and there was, in some sense, the idea that the strong interaction were described by some theory that was strong at all energies. Therefore, the large energy, you should go for strong interaction to some non-trivial fixed point. So if the trivial fixed point things were if the fixed point were non-trivial, there was the idea that there should be scaling violation. You should see the enormous dimension of the various things that were present in the theory in deep inelastic scattering. And we did I did the work on the dimension, on how to do the measurement of these dimensions, enormous dimension of the field in deep inelastic scattering. And after the year when QCD came out, I started to work on QCD. And therefore, I did the first computation on violation of deep inelastic scattering for QCD in 74. Just after QCD, we went on with Roberto Petronzio on discussing these things. And this was very important because I learned a lot of phenomenology about the QCD prediction for deep inelastic scattering, and we start to write some kind of evolution equation for the evolution equation for the effective quark distribution for the quark structure function. However, the paper that was very important was Altarelli Parisi, that was 77. In Altarelli Parisi paper, asymptotic freedom in parton language, this was essentially a breakthrough because we write in a clear way the evolution equation for parton distributions. And this was the starting point. In all other papers that came out in which people started to compute the other processes in high energy physics, in proton-proton collision, proton-antiproton, and larger angle scattering, and also X production and so on. And I think that was and now this Altarelli Parisi paper contains a change of viewpoint, because in all previous papers, the deep inelastic scattering was studied using Wilson expansion, therefore something that was not very intuitive. In Altarelli Parisi paper, we use the computation in a very simple way, and essentially using the infinite momentum perturbation expansion that we were that I used in 72, 71 paper with Givilli. I think that Nicola Cabibbo had a very enormous influence on this field, because he stressed the importance of infinite momentum perturbation expansion, and the paper of Altarelli Parisi was very similar to a paper of Nicola Cabibbo and Rocca that he published 1 year ago on electrodynamics. I was interested and continue to be interested in this field, and one thing that is a nice remark that was done by Altarelli on this paper, that this is the most quoted French paper on high energy physics, and you call this French paper because it was written at the moment where myself and Guido Altarelli were in Paris. And now, in the same moment, the same period, I was very interested to problems that were connected to quantum field theory. For example, there was one paper, Value of the Fundamental Constant, in which I was doing some renormalization group up to the gravity scale. This was something that was done essentially similar to the people that were doing SU5 unification. The only difference from that I was doing SU5, that I was doing this unification sorry, I was looking to the different coupling on the theory, electromagnetic, strong and weak interaction SU2 plus U1, and the idea was if all the interactions were strong at high energy, if one could fit the idea that the moment where gravity is important, which 10 to the 19 GeV, all the constants were equal. Now the things was possible to do this, putting all the theory together in this way. The only problem that I have to introduce 8 or 9 family of different quarks, neutrinos, and so on, which was a very large number. We did the same computation with Mariani and Petronzio in 78 using supersymmetry. The number became different, and the thing that was finally interesting was in the same spirit of the previous paper was a paper that came with Cabibbo, Mariani, and Petronzio, in which we put some bound on fermion AX in grand unify in different kind of theory, and at the end we were quite happy because we argued at the end that the X should be mass should be 120 GeV and 200 GeV, and we were very happy that the value of the X max just came in the right bound. Now, there have been 2 papers that have also been important on quantum field theory at that moment, quark imprisonment and vacuum repulsion. This was something that comes back to something that I learned when I was studying superconductor. I learned that studying superconductors that you have a flux line, especially in type 2 superconductors. And in this situation, the idea was what happens if you put a monopole or 2 monopole, anti-monopole pair inside the superconductor. The monopole field cannot be shielded by the superconductor, therefore you find a flux line between the 2 monopoles, and that is some model that you can think in a simple way to get confinement. The paper by with Guido Parisi, Exponential Hadronic Spectrum and Quark Liberation, this was probably the first paper in which we discuss about the new phase of quantum matter, hadronic matter, and high temperature. And it came out when we were in Irish to the conference, and during the conference we sat together with Nicola and started to discuss about the possibility of having a phase transition in a theory of strong interaction. And because the spectrum of resonance and so on were suggesting the possibility of having a phase transition, and finally we wanted to interpret this phase transition as quark liberation. So, and I started to be very interested that time to things on lattice. There was a paper that we had, and also to high temperature expansion, because high temperature expansion, I realized, was the other way to compute critical exponent. So critical, the fact that it was interesting to precise value of the critical exponent, it made me very interested to lattice. And for example, we did 2 papers with Benzi and Martinelli on high temperatures, tried to remove lattice with perturbative expansion. In the period, I did a work on Amati, Ciafaloni, and Marchesini on region field theory. I knew very well region field theory of Gribov because it was all the approach of Medallic-Kadanoff to critical exponent, starting with the work that I did with Gribov. And I was trying to understand also strong coupling lattice case theory, and we did a paper with Luff and Sourlas that had a very important, at least for me, on computing what happens lattice case theory at large dimensions. So this was not this type of work that I did. I get some knowledge of field theory on the lattice. Well, in '76, there happened 2 things. Once that I went to Paris, and the other thing that there was just in the same moment, went to Paris to appeared a paper by Lipatov, in which Lipatov discovered that one can compute the behavior of perturbation theory at high orders. When I read the Lipatov paper, it came to my mind that the content of the Lipatov paper was more or less, but framed in a slightly different way. The technique were the same technique that Langer in the paper of 59, etc., and so on, was trying to study non-perturbative effect and tunnel. I remember quite well that when I seen a Lipatov's paper, I compared to Langer, and when I read Langer, I dismissed the computation that was essentially done by Langer of large order perturbation theory, because I thought that it was that was too simple and was probably not correct. I mean, it was just an impression that you get reading a paper for 20 minutes. You may quite easily get the wrong impression. So I started to try to put together the Langer paper and Lipatov, and this was the first paper that is there. And the other thing that was interesting, that I tried to rederive Langer Lipatov result for first theory. And finally, what I did was something that I did not realize what was. Essentially, what I considered a Feynman diagram as a beta lattice, and I was started to do cavity expansion from these things here. It is quite amusing that when I started to study beta lattice again 10 years later, I completely forgotten that I was doing cavity expansion at Z in this type of model, and I rediscovered only a few years ago that I was doing these things. Now, I realized that at that moment, the whole things was done by bosons, and therefore, nothing was done with fermions, so I had to start how to do fermions. I was familiar with, I was quite familiar with the fermionic path integral formulation, the possibility of integrate over fermions direct in quantum field theory. So at the end, I did this paper, which I showed how can you estimate large order perturbation theory with fermions. And in doing these things, I have to learn many things, better how to deal with fermions, and a lot of things about the entire function and so on, large order behavior on entire function. Of course, after we did the same job with Simpson and Zuber from quantum electrodynamics, is working with these people that have a much better mathematical information than myself. I learned a lot of things about other things about entire function and so on. And of course, I started to go to work on these things with Brezen. For example, we wanted to do compute the prefactor, and that was a quite complex computation. And of course, I tried to expand this type of estimate and perturbation theory, not only to problems that were caused by instability, but to try to understand also the other problems that were related to large momentum behavior to the normalization group. At the same moment, we start to work with Brezen, Higginson, and Zuber on planar diagrams. And there I learned a lot of mathematics about matrix model. Just to, I have some recollection of the moment that we were working together. Usually myself and Jean-Bernard Zuber were taking the same subway to go into Saclay, where we're working together. And we start to work for half an hour more on the subway. Therefore we arrived there with something done. And most of the work was done on the blackboard, as usually. And there was some rotation that 3 of people were working on the blackboard. One was usually taking notes. And I remember that I was forbidden to take notes because my notes were too bad and were not comprehensible. So anyhow, I started to, this was a wonderful experience also for the personal viewpoint. And one of the things that I was starting to reflect how to go to strong coupling, and I was interested also to resummation technique. And there was a paper that I wrote in 78, but it remains manuscript, in which I remember that I was saying that, well, a lot on the introduction, that a lot of progress had been done going, taking something that was integer, going to non-integer. And this was done by Reggie Paul, that making analytic continuation to non-integer, to complex values, the angular momenta, obtained lots of results. The idea of taking non-integer dimension of Giambiasi, Wilson, and so on was very interesting. So I was discussing if one could generalize perturbation theory to non-integer order and see the type of behavior of perturbation theory and non-integer orders. This was quite interesting because that was never written, because I started to be interested to something a non-integer value in a completely different context that were, let me jump these things, and this was a paper, essentially the paper on spin glasses. And now you may ask how happened that I started to work on spin glasses in 79, and the reason was essentially connected to this paper, strong coupling phase in lattice case theory in large dimension. Now, what may be the relation between gauge theory and large dimension and spin glasses? Well, apparently there is no relations, but the things that we did in that paper, that we showed that for lattice gauge theory, the leading term were essentially given by some kind of branch direct polymer. Now, if we want to understand the subleading correction, we have to compute loop in theory of branch polymer. And I looked on the literature when I came back to Rome, and I discovered that there was a lot of work that was done on this type of problem, essentially by Lumbensky. And Lumbensky were mentioning that the Sherrington-Kirkpatrick model was studied. Lumbensky mentioned first all the replica method, and however, the replica method for the kind of problem that Lumbensky was using was something easy to understand, because it was essentially a generalization of the replica method that was used by the Zhang for polymer. This was used for branch polymer, and he says that, however, that one should be very careful with the replica method, because the replica method, in the case of Sherrington-Kirkpatrick model, gives a wrong result. Now you have so I started to look on Sherrington-Kirkpatrick model, and I was not at all interested in spin glass. I had no idea what spin glass were about. However, I thought that there was a shame that some method that I liked, that was very nice, like the replica method, in some case were giving wrong result, and one should understand why there is. I think that was a duty to understand why the results were wrong. And I thought that I should spend some of my time in the beginning of 79 to try to fix what was wrong. And I started to work on spin glass, thinking that the things should be relatively easy, and that there should be some relatively simple mistakes in the computation, because the computation was Sherrington-Kirkpatrick, and the final result were clearly wrong because the entropy was negative. The point that it turned out that there was some wrong assumption, and the wrong assumption was about replica symmetry. The method Sourlas had already shown that the replica symmetry should be broken, and it was not clear how to do. I mean, I started to work on the field. At a certain moment, after a few months, I understood how to break replica symmetry, and after I wrote something about 5 papers on spin glass, one after the other one, and I think that in doing the work on spin glass, there have been a few things that have been quite helpful to me. First, all the work that I did in quantum field theory, starting from Parisi tests and so on, was all the knowledge that I had of replica symmetry breaking, of spontaneous symmetry breaking in field theory, group invariance, the fact that when you break a symmetry group, the symmetry group must become smaller, that you have I mean, all the type that you have Goldstone boson and so on, that the fact that, okay, therefore all this type of, this was quite useful. And also it was quite useful the idea that, as I told you, I already floating around that one can think to what happens to non-integer value of Saint-Just integer, for example, perturbation theory at order 1/3 for scalar theory and so on. So the idea, so the things to go on from scalar, from integer value to non-integer value, because at that moment in this approach, some of the parameters have to take a non-integer value at the end. In my approach, it was something that was quite useful. And however, these papers were written, were done practically completely ignoring the physics of spin glasses, and also it was not clear at all what the physics of spin glass was about. And however, I came back to, in '82, to the problem, also because I had to write down a lecture notes for the source. And I realized that there was a precise probabilistic interpretation of the parameter for spin glasses that was a function Qx. This was quite unexpected, because in these things, the spin glasses, the other parameter is a function. And I realized how to give a probabilistic interpretation of this function. And after I started to work with my friends that were at that time in Paris, Miguel was in Rome usually, but I started to work on this field when he was in Paris. And therefore we studied all these probabilistic interpretations or probabilistic result for spin glasses. And in a paper that was very interesting with Mezzar and Miguel, we were able to formulate all the spin glass theory in terms of probability theory. And however, in the same moment, in the same things, I was also doing other things. Probably, I was, as I told you, I was interested from the beginning to Langevin equation. My interest in Langevin equation grew up after a paper by Brezen and the Dominicis on the dynamics for on the dynamic approach to second order phase transition to the problem understanding dynamics in second order phase transition. There was a lot of things that were important in this case, and also there was something that it was quite important that I learned during my study of critical response. It was an observation that I think that was done by De Croisseau. I'm not sure about. Essentially, well, what people discovered that when people were doing the expansion for critical exponent, the number of dimensions of all fields had a factor n-2, where the theory was a ON symmetric theory with n bosons, and when n was equal to -2, all the things disappeared, and the things that was realized that with n, that two negative number of bosons, -2 bosons, were equivalent to fermions, and just because the theory was a 5⁴ theory, for n equal to -2, this was a 4 Fermi interaction of the same kind, and this was automatically 0. So the idea that the two bosons were equivalent to 1 fermion is something that was floating in my mind, in our mind, coming from from work on that other people that have to study on critical exponent. And when you try to do these things on saying, well, maybe to both dimensions were equivalent to 2 fermionic dimensions, and we knew that the fermionic dimension were related to supersymmetry, and that was essentially the origin of the paper that we did with Nicolas around the magnetic field, supersymmetry, and negative dimension, which was a way to derive in a very compact way the dimensional reduction that was done by other people before us. And now this being me an interest on stochastic differential question. This interest on stochastic differential question was quite important because we did with Fucito, Parisi, Marinari, Rebbi a proposal for Monte Carlo simulation of fermionic system that was based on stochastic differential question, in this case Langevin type, and the paper that I did in the same period with Urion Shea on perturbation theory without gate fixing was still based on Langevin equation. So you see that you get these 3 papers that were quite different, that were have a very common background, that is a stochastic, the things of stochastic differential equation, and the work with Sourlas with negative dimension is connected with the work that was done with the other things. Now, I started to be interested, I think, with doing Monte Carlo. I think that the first Monte Carlo simulation I did was with Sherrington Kirkpatrick model, because there was one crucial property of the theory, the prediction, that I want to verify, and therefore I had to be sure that it was correct. I studied, did the Monte Carlo for the Sherrington Kirkpatrick model in magnetic field, and that was my first Monte Carlo. I learned to do Monte Carlo. In a very interesting paper that we did on Fermi passa Ulem with Fucito, Marchesoni, Marinari, Peliti, and Ruffo, and Vulpiani, we started to do, I learned how to do molecular dynamics. And also, I was very important that in this paper, we were stressing the role of complex singularity. Now, this was starting to do my interest in computer, in doing fast computer, writing fast computer, and because we want to do large scale Monte Carlo. We started to do Monte Carlo with Martinelli and Petronzio on the 2-dimensional nonlinear sigma model. And I did also some other Monte Carlo. And after we started to do Monte Carlo with Falcioni, Marinari, Pacella, and Taglienti, and you see that here you don't only you have the theme of Monte Carlo that comes back again and lattice gauge theory, but also you have the theme of complex singularity, because I was interested in the same moment of complex singularity on Fermi passa Ulem, and we had wrote a paper on complex singularity in lattice gauge theory. Now, while in the Fermi passa Ulem there were complex singularity in expansion of space, in Fermi, in the paper of Falcioni, complex singularity was in the temperature plane. And of course, we went on doing Monte Carlo with, this were Monte Carlo with scalar field. However, we started to do in the same year large-scale Monte Carlo for four-dimensional theory in the quenched approximation. The name quenched approximation is taken out from spin glass because, we did a paper in quenched approximation with Marinari and Rebbi on SU3. SU3 we did with Humber, and we did a lot of papers on quenched approximation with other people. Let me just go to Martinelli, Petronzi, and Rapuano paper. And everything was done on lattice that were very small. I mean, because computers were done sometimes on a box, sometimes on a cray, but it was 5 to the cube, 6 to the cube lattice, 5 to the 4, 6 to the 4 lattice, which are much smaller than the lattice that I've done these days. So, and at the same moment, I was, okay, at the same time, I was interested in other problems that, well, this was something that was more, if you want, sporadic, because the paper on stochastic resonance in climatic change arose after a seminar that was done by Alfonso Sutera in Rome. And after, I remember that he had a long discussion on tramway in Rome where Alfonso was going home, also myself at Rome, and taking, starting from his seminar, from discussions that we had on the tramway, we wrote this paper with Benzi and Vulpiani, but most of the work was done by them. I was only starting, I did a very short amount of work on this, but it was just a starting point. Also, the paper with Fritsch Parisi on the similarity structure of fully developed turbulence was quite amazing, because we were in Cargese in 83. Fritsch made a seminar, and after the seminar at lunch, Uriel, which is here, I had a long discussion on him, and we had this idea of multifractional nature of turbulence. And I mean, I think that I said to him quite immediately the fact that the experimental result was showing that there were fractal of different dimensions that were nested one into the other. And I think that introduced the idea of this, of some kind of Laplace transform or Legendre transform to get a spectrum of singularity. And Uriel was very kind and did a grateful gift to me and also to other people, writing a small chapter or two-page chapter on the book, where these things was the result of the discussions that we had together, was written in a clear way, in such a way that we could not forget. And these things, after we studied in great details with Benzi, Giovanni Paladin, and Vulpiani, and where we describe in great details the multifractal nature of turbulence and how all these things applies to also to chaotic systems and so on. However, let me come back now to the lattice case theory. Of course, the lattice case theory, as I told you, there was a problem of doing computation, and the problem of doing computation was solved in some drastic way, that we decided to construct a computer at home. Therefore, we put, this was something that was started in 1984. It was Nicola Cabibbo that had this idea of constructing a computer. And we started a computer that was Ape. Ape was a very great success. It was a parallel computer that could write to a gigaflop per gigaflop speed and a gigabyte of memory. Of course, that was is completely unimpressive nowadays. I mean, I think that a smartphone is much faster, has much more power, memory. However, at that moment it was quite impressive. I think for 2 months, it was the most fast computer in the world. And we did a lot of paper, and I wrote up a collaboration, because after I don't want to fill the slides with names, but the names I want to change. And one on group bond masses, hadronic mass spectrum, and we started to do a upper 100 project that I started only, but was not involved. And this was for call upper 100 because it was 100 times faster, and that involved the construction of some special chips. So this is something that on which I was working mostly on these things for 6 years. And as all type of byproduct, technological byproduct, people that learn to do, I mean, also for industrial product, software house and so on in Rome and in Italy. And this was also a great fun. Now, in the same time, I was working with Zhang. And Zhang, the things that we want to understand, what's happening to some models. For example, Eden model was a model of tumor growth. I think that I was interested in this model because I did a paper with Nicolas Sourlas on some other model of random animal, which everything could be computed by supersymmetric. Therefore, we try to start to understand Eden model in many dimensions. This was something that was connected once again to this paper. This paper here, strong coupling expansion in large dimensions. There was the idea that one could do some computation in lattice theory in large dimension. We wrote this paper with Eden model. However, the thing was not very successful because it was not possible to resum the expansion from large dimensions. There were non-perturbative phenomena that could not be controlled in the large dimension expansion. We started to try to understand that this may be used for diffusion limited aggregation, but this was not very useful. At the end, we found with Kardar a very nice application of this. This idea, however, was not, the things completely changed. At the end, it was a dynamical equation wrote directly in 2 dimension, 3 dimension. And what people call it on the KPZ equation for growing interface. And however, this naturally comes out on the work that was doing with Zhang and with Zhang. It's quite interesting that Zhang at that time was in Boston, I believe, and they just came back to Rome. And after lunch, we had some discussion on interface. And I wrote something on a book note. I think that it showed me that he still have the things that I wrote on book note. And after, when he came back to Boston with Kardar, they did the great part, the whole bulk of the work with lead to the KPZ question. Now, in the same time, well, it was not true that I was only doing lattice gate theory. There was some work that was doing with well, with Mezzar, and also there was a paper I mentioned already with Virasoro. On that was a lot of work was done in replica and optimization. Was a replica optimization. We started to do matching problem. And after we studied the travel assessment, of course, we were doing in mean field theory, we start to study this problem in finite dimension to see if there's some correction, which has a correction to mean field theory. We started to do replica field theory with random manifold. And after we start again, after a lot of time, to think again about better lattice spin glasses. And therefore, this was something that was a very influential paper, the one that we did with Mark. And because it was showed how you can do replica symmetry breaking on a lot of models that were very interesting, not only spin glass model, but a cavity equation. And the thing that was came out was that this could be done with for the KSAT model for random satisfiability problem. And this was we were able to compute this was a problem that was very interesting. People doing mathematical, not mathematical physics, but computer science were very interested. And indeed, we did a solution of this model of the random strings that finally, after 10 years, at least in some particular case, people proved that was correct. I mean, I was also interested in this time on application to biology, essentially to neural network, to monological network, and I was working for that time. And however, in the 90s, more or less when the work with Apple was running down, I started to do again, Monte Carlo for the for spin glasses. I think the first paper was with Caracciolo, Paternello, and Sourlas. And after with Enzo, we started to do, we wrote a paper simulating temper. Simulating temper was not our invention, but however, we used a lot, and we did a lot of work with many other people, especially our friends that came from Spain. And that also there was a very important collaboration with Spain that was started with the Apple project with Fernandez Tarazon, and after it went on with Felix Ritort, with Lorenzo, and Vito Mayor. And at that time, we did a lot of numerical simulation for spin glasses, and this was one of the main activity. And we want to understand it to see if one can see thickness of spin glass symmetry breaking in 3-dimensional, 4-dimensional. We wrote also some long paper where we put both theoretical foundation and numerical evidence together, and also in another situation. And we want to also to understand some theory, and also which was in lower critical dimension for spin glass. And there was this suggestion with Franz and Miguel, Silvia Miguel, of dimension 2.5 for lower critical dimension. And was a very interesting paper, I would say, with Franz on receipt for spin glasses. Essentially, they were more used for glasses than for spin glasses. And they were the basis of what people later on called the Franz Parisi potential. Now, at the same moment in 94, I start my interest in glasses. There are 2 papers that I did with, sorry, not in spin glass, but in real glasses. There were 2 papers with Marinari and Ritort, in which we could show that replicate ideas could be used successful with models which were not random. And I start to play with the idea of equilibrium fluctuation dissipation in glasses. We did some analytic computation with Mark, which later on was done with Colucci, and the other type of computation was done with Lanina and Grigera and so on. So there was all this interest in theory and theory on glasses, and what happened at a certain moment in 2005, I open a parenthesis. We started with Nicola Cabibbo to 2006 maybe to look to something that was completely different. That was Starling of flocks, and we did a real experimental work. And I think that the origin of this work were some discussions that we had with Renato Sarno, Walter Tross, Todesco, and so on, when we were doing the upper project, but realized that at that moment it was impossible to do these things in natural way, because one had to deal with an incredible large amount of analog photograph. And in 2006, when 2005, when with the photograph, we had a good digital camera, we studied this type of object, and and that was something that we've been working on. Now, at that moment in the order of 2005 and 2006, we realized that the standard computers were not enough to do numerical simulations for spin glasses, and therefore we started with a Janus collaboration, which was essentially from Rome, but it was Ferrara and Spain, and we did a dedicated computer that was based on PAL, and this is a list of people that worked in the first paper. The list of that we did about 10 papers on the Janus collaboration. The name changed, but I could not reproduce all the name in later paper because it would take too much space, and therefore we started to do spin glass at fixed temperature, and all of this type of work that was very delicate. And the thing that was quite interesting for this computer, that we could do this type of Monte Carlo simulation for a time that was quite long, was order of 10 to the 11, 10 to the 12 Monte Carlo step. And this meant that we could do this work for, just if you think that one Monte Carlo step may correspond in reality for spin glasses to 1 picosecond, this means that we could arrive to a fraction of a second. Therefore, we have an incredible large view on the dynamics that was 11, 12 order of magnitude, and we can just arrive to nearly to the situation where real experiment change. A real experiment start in the range of 1 minute. So there's a small gap between this microscopic and macroscopic and the real experiment, but this was fundamental. And this was extremely interesting in consolidating all the ideas that we had of spin glasses. There was another type of work that I was doing at that time. There was the idea that all paper that we did with Mark, Colucci, and Verrocchio, and so on glasses could not be done for R sphere, because R sphere were much more difficult. And therefore, I get a very smart PhD student, Francesco Zamponi, And with Francesco Zamponi, we have been able to solve the problem of doing the same computation that we did with Mark for the case of R-sphere. And therefore, this started to do our collaboration for R-sphere. And we started to be interested also in jamming. Therefore, we wrote 2 papers with Jorge Francesco, started from 2012. After there was 1 paper which I'd also Patrick Charbonnet and Pier Francesco Urbani. Sorry, Pier Francesco was also in the 2nd paper. I'm sorry, I forgot the name. I apologize. And the thing that was very interesting that we discovered in this thing that there was something completely unexpected. There was a Gardner transition, and that we could compute the critical exponent for jamming. Now, that was something very, very important because we could show numerically that there was good evidence of Gardner transition. It was quite impressive that the computation of the critical exponent of jamming. And because they had in a perfect agreement the mean field result with the result of the numerical simulation, also because the critical exponent of jamming were irrational, and this was the first case of irrational mean field exponent. I'm going very fast on more recent things because I think that most of the people knows much better recent stuff than old stuff. And now I am nearly to the end. I would like to mention that some other works that I did, bipartite entanglement, that is something that I did with our friends from Bari, and mostly from Bari at the time, and on entanglement, well, maybe Scardicchio or Antonello maybe was in the United States, and that was using our own idea that had a statistical mechanics to do something that was completely different from quantum, and we did a lot of work to try to understand many of the open problems that were still there with the people in Rome, and these are some lists of some of the most relevant papers. Of course, clearly that there are many, many other papers that I would like to quote, but there was some constraint of space, some constraint on time, and the only things that I would like to finish with a big thank with all people I was lucky to work with. And let me present a list of 317 scientists I worked with. It is updated up to 2018. The size of the name is roughly speaking proportional to the number of people together, and all the other scientists and many more for which I've been collaborating in an indirect way by exchanging results and so on. So thank you very much. I finished my talk. Thank you so much.
Thank you, Giorgio.
Thank you, Professor Parisi, for a fascinating lecture. It was quite amazing that we got a glimpse of all the wide variety of things that you have worked on, and you have made very important contributions, and how all these different things are related to each other in some way or other. So I think that was really a fascinating experience. I think we can take some questions now. Professor Parisi, you will be available for some questions, right?
Yes, please.
Yeah. So those who want to ask questions can use the raised hand feature, and then we'll go through them one by one. There are not too many questions from chat or from the YouTube. So we'll first take the questions, people who are live on this session. So Sventa.
Hi, hello, Giorgio.
Hi, nice to see you.
Yes. During your talk, one question occurred to me that you never worked on quantum gravity or those areas. Is there some, with your breadth and depth, you could have definitely made some contribution.
Well, I started to look. I started to look on quantum gravity in the work that I was doing in the 90s with the work with one-dimensional string, non-perturbative correction to quantum gravity. But at the end, I thought that the problem was too difficult, and there were excellent people working, and I thought that maybe I should find some other subject with less people working around. And for a certain moment I was reflecting, but I had no great idea, and there was a lot of things that was already done, and then no great idea came to my mind.
Okay, thanks. Thank you.
Okay, other questions? Please raise your hand if you have any question. Yes. I have a question from Eric Orel. Please unmute your mic and then ask the question, please. Eric.
Yeah, now
Hi.
managed download. Hi, Giorgio. Thank you for a fascinating talk. Can I congratulate you once more on the prize? It was wonderful. I thought it was very fascinating, the timeline in 1979 when you made the discovery of replica symmetry breaking. You said you started in early 1979 and the first paper was submitted to the journal in April. So you cannot spend more than like 3 months on the first calculation. It would be nice to hear also, I think, for the younger people in the audience, a little bit more detail on how it actually happened.
Well, in reality, I started to work on just before Christmas vacation in 78. The paper was submitted, I think, in April 79. I think that for the first 3 months up to March, I understood a lot of things. I recovered many of the results that were obtained by other people, but I had not any idea how to go on. And after discussing with some people in a meeting at ICTP, I got the idea of taking some variable, in that case m, to non-integer value, and that completely changed the things. So after the first step, everything was relatively easy.
Hello, Eric. Your question is answered, right? I mean, so we can go on to the next one.
Yes, I think I answered. Or you want to have some, maybe I misunderstood you, Eric.
Oh, he's muted for some reason. So I think his question is answered.
I think that answered.
So we then go on to Bellar Shiva Prasad. Mr. Shiva Prasad, Dr. Shiva Prasad, please, can you unmute yourself and ask the question?
Yes, it was a very interesting talk, but what I want to ask is, I don't have to tell you that climate is a very complex, highly nonlinear system with multiple dimensions, multiple scales, both spatial and temporal, varying from nanoscale to terrestrial scales. That being the case, can human beings change the produce enough scales or enough turbulence to create order in this system, which of course scientists, of course, like many of the scientists, including yourself, have predicted global warming. Can they produce order and a predictable order to produce global warming?
Well, I mean, although I did the stochastic resonance to studying climate model, but in that moment I was interested to glaciation, not to warming. And I think I'm really not an expert on global warming. I think, however, that the people done the computation have been very successful, and they are refining this computation with great details. They are going to something that was somewhat approximated to something which is better and better going with the time, and and what is very important, reducing the interval of the confidence interval of their prediction. Of course, it's clear that we have to understand things on many different scales. There are something that is missing, for example, with the details of the atmosphere ocean interaction. We do not really understand in details how the ocean absorbs CO2. And this is something that people are doing. For example, there are a lot of ships that are going inside the present moment in the oceans to measure the amount of CO2 at different level in the sea and so on. Therefore, it's clear that it's something that is very complex. There's many different concepts arriving, and people are doing a magnificent work to cleaning all different subjects. I mean, to different corners of the argument, so on.
If I can follow up and ask a question, I mean, I would say stochastic resonance, even if there is any resonance in any nonlinear system, that cannot lead to predictable continuous variation of one parameter like temperature. And see, what is being predicted is a global warming, which of course in my view cannot be predicted in this multi-dimensional, multi-physical system. And they're predicting global warming. Can those predictions be? See, we can't predict turbulent flow or even a simple flat plate if there are multiple physics or multiple scales.
Hello, can you keep your question short? I mean, there are many other people who are waiting. So.
Well, yeah. Do you believe in this global warming prediction with so many scales, physics, and all those things involved?
Look, first of all, global warming is not my field. What I've seen the paper of these people, seem to be extremely high professional. They've been controlled, so I have no reason to doubt what my colleagues are saying about global warming. But I think it's not a good moment to discuss global warming. You should discuss with the other Nobel Prize, not with me.
Okay, thanks. Yeah. So I go on to the next question by Berenguer Dubrubel. I'm sorry, I probably am not.
Hi, Giorgio.
Hi.
You mentioned that you did only a very short but very fruitful incursion in turbulence. And in your talk, you mentioned the problem of complex singularities in some problem. And what about in turbulence? If we had complex singularities, how would they see us? You know that there is a problem of singularity in Navier-Stokes equation. And in your opinion, if there were not real singularities, but say complex singularities in Navier-Stokes, how would they manifest, for example, on the multifractal spectrum? Do you have any intuition on that, or you never also?
No, not really. I think that is something that I discussed at length with Uriel, but had forgotten the conclusion. But the question is certainly very interesting. But I mean, I think that Uriel did work on complex singularity. I think that the complex singularity are very important near the viscous range, the end of the range in momentum spectrum, near where it's dominated by viscosity. But I completely, you should ask me this question 10 years ago, 15 years ago.
Ah, too bad.
But you can now ask to Uriel. You can ask to
Uriel also, he say, oh, okay.
Okay.
But you know that now they have discovered a singularity in Euler. There is now a proof from last year.
Yes, that I know.
Okay.
Okay.
Thank you.
Okay,
Thank you, George.
We go on to the next question by Mr. Raghava Krishna, sorry. I'm sorry about it. Dr. Raghava Krishna, you were online. Please unmute yourself and ask the question.
Am I audible?
Yeah.
Good afternoon, sir. I consider this to be a great honor to speak with you. I have a short question. What do you consider to be the most appropriate method that can be used to model the turbulent diffusion of electron-positron plasma in the lobes of radio galaxies?
Well, I have not the slightest idea. I mean, astrophysics is something which I never learned carefully, so don't ask me this. I don't know.
Okay, thank you, sir.
Yes, so I'll go on.
Anyways, congratulations on your prize, sir.
Thank you.
Then Dr. Bamba, Bindu Bamba. Please unmute yourself. Yeah.
Am I unmuted? Am I audible?
Yeah, we can hear you. Yeah.
Professor Parisi, I have been a great fan of your work.
Thank you.
Many years. In fact, in 1983, when I visited Rome, I went to the university, but you were not there. I went to meet you. But I want to, some of the papers that you mentioned, I was not aware of. The paper on quark liberation, did you actually predict a quark-gluon plasma in that paper, or was it just asymptotic freedom?
No, we predicted in the paper with Cabibo a quark-gluon plasma. Yes, I think, certainly predicted that at higher temperature, we were using maybe gluon, maybe not, but the quark plasma, yes, certainly. The idea is that, for example, if you think of some model in which the hadrons stay in one bag, you would have the coalescence of the different bags of hadrons, and therefore the quark should be moved. Therefore, quark liberation means quark plasma. I don't remember if we said something about gluon, but we want to be, I think, to be quite general that this phenomena should happen both in theory with gluons and both in theory without gluons. But if we mention, I don't remember if in that paper we mentioned gluon, but certain quark liberation meant quark plasma.
Well, that's very interesting because it should, I mean, that may be the first prediction. But also one more question. In your interface, dynamical interface model, is that related to diffusion limited aggregation? And if so, did you find a fractal structure also?
Well, the point that the diffusion limited aggregation is something that is one of the problems that troubles me, in the sense that I would like to understand the diffusion limited aggregation. I wrote some short paper on it, but I never had a good understanding of diffusion limited aggregation. And that is something that I'm sorry about that, but the point that for which a diffusion limited aggregation, I think that is very interesting, is that it's not clear which is the upper critical dimension, if there is an upper critical dimensions. And however, I tried to attack the diffusion limit aggregation from different viewpoints, but I was never able to arrive to any good result.
Thank you. I hope you continue with DLA.
Okay, so then we go to the next question by Qazi Islam. Please unmute and ask the question.
It's an honor to speak to you, sir. I would just like to ask you, could you provide some more insight into your thought process? For example, as I see it, you have worked on various diverse fields and often found it fruitful to, combine techniques you learned in them. So are there other such things that, helped you make the discovery?
Well, I have not understood exactly the question, which was the final part of the question.
Yeah, so what I'm basically asking is, what do you think helped you make the discovery?
Well, I think that one thing that was crucial was curiosity. I mean, I think that the most essential things was curiosity, but apart, of course, you may be curious and you have to have the tools and also the things that comes out that something that you observed in a faraway system may be very useful to arrive to the result. And the simplest case was this observation of having trivial critical exponent for n theories n equal to -2 was connected to dimensional reduction with Sourlas. So you get connections which are different from different things, and understanding of fermions that I had for looking for high order perturbation theory was important for for understanding how to do simulations with fermions in gauge theory.
Okay, so I think we'll go to the next question by Deepan Betal. Please unmute. Deepan Betal, are you there? Hello? You're still muted. Can you unmute and ask the question, please?
Yeah, unmuted, but I think he's not at this speaker.
Yeah.
Maybe microphone is not fully working.
Right. So you may write it down in the.
He has written the question.
Okay, so I'll read it. As in ADS-CFT, a conformal field theory without gravity gives predictions for a gravitational bulk. Would the bulk theories inversely be used to give predictions for a CFT and perhaps a complex system without gravity? So it's a long question. So, I mean, do you want me to read it again?
Well, the point that, as I told you, I really do not expert on gravity. I mean, I follow some. What I was interested in some conformal theories of the more conventional type that were the conformal theory, which were scale invariant for second order phase transitions. Therefore, the ones that were relevant in statistical mechanics, where gravity did not play a role. Of course, there's a lot of things in conformal theory that have been quite important in recent times. That was a bootstrap that was done, and also there was discovery of an expected theory in more than 4 dimensions by Klebanov and so on. But as far as gravity is concerned, I'm not the best man to ask question.
Rajesh, can you unmute and then ask the next question?
Yes, thank you very much for that very stimulating talk. It's a sort of follow-up on the previous question you mentioned, and you did just now, also about this revival of the conformal bootstrap, which you had worked on 40 years ago. Sorry, more than probably closer to 50 years ago. But these new techniques, do you feel that you can access problems that you could not earlier? So where do you see the new bootstrap techniques and the improvements being able to address questions that you think you could not at an earlier time, but which you feel are now potentially tractable?
Well, there's few things that, first of all, there was this magnificent result of that with a conformal bootstrap, we can have the know the value of the critical exponent of the three-dimensional Ising model with 5, I think, decimal place. That is a completely unprecedented result from something numerical computation, because other type of techniques were much as 3 decimal figures, and therefore this is extremely important. And I think that something that should be done that will be extremely important is if one could generalize the conformal bootstrap in the same effective way to theory which are non-unitary. Let me explain. I mean, when you take a problem of statistical mechanics, sometimes, sometimes it may be represented as a model of or as a field theory model in you have a d-dimensional, let's say that you have a 3-dimensional Ising model, may be considered as a field theory in 2 + 1 dimension. Now, many often you can do this type of job. It's the contrary of the weak rotation that one learns in quantum field theory. And when you do this rotation, some model like the Ising model are unitary model. If you do the same job, the same rotation for percolation, you can write a theory for percolation, field theory, but the field theory is not unitary. Now, the thing that will be, now the way that the conformal bootstrap has been done, it use in a crucial way, the technical but crucial way, the unitarity of the theory. The fact that the theory after rotated is in unity space, which means that a certain number are positive. And the positivity of this number is something that is very relevant. If one could be able to use, maybe not with 5 decimal figures, but with 2 decimal figures, the conformal bootstrap, for example, for percolation, which is a very interesting problem, that would be extremely interesting. Also, there are a lot of problems that, for example, that are supposed to be conformal invariant. Spin glasses, and also, for example, the turbulence itself has been discussed many times if it is conformal invariant and not conformal invariant. So, and the turbulence certainly is not related anyhow to some unity theory with a weak rotation. So, there are a lot of things that could be done by conformal bootstrap if one could have something less precise but working to control this theory. Also, for example, KPZ, the question of growth processes, the way one could think of conformal invariance in some of DLA and so on. Therefore, it would be extremely interesting if one could extend this kind of result to other type of theories which have nothing to do with conformal, with a unitary theory.
Yeah, no, that's a very crucial point. Thank you again for the lecture and for being with us.
Thank you.
So one more question from one of the organizers, Abhishek.
Yeah. Yeah. I have also a question.
Yeah.
Thank you.
Yeah. So, Abhishek, you go ahead and then I will ask.
Okay. You go ahead, Saurajit.
Okay. So, Giorgio, this is related to this recent work on swap, Monte Carlo. And then this, because of this massive speed up, Mike Cates and Matthew Via wrote in a couple of papers saying that so the glass transition probably is there is no static correlation, which is probably playing an important role. And then there is a subsequent kind of reply back to this argument by Giulio Biroli and Ludovic and some of the other people saying that no, that's not necessarily true. So what is your opinion on that controversy?
Well, I mean, I'm not followed in great details, but I think that as far as I remember, the answer to Giulio was convincing to me. I had forgotten the details. I regret that I'm not able at that moment to explain why the answer of Giulio, but I think, but I have some recollection that I agree with him.
Okay. Yeah. Thanks. Yeah, there are some controversies which are going on, and so maybe that is something which is probably of interest maybe in future as well.
Okay, but anyhow, I will look later on. I will look more in details, try to refresh my memory.
Okay, please. Yeah, thanks.
Abhishek.
Yeah, so Giorgio, I mean, you have worked on, like, you have thought about this problem of ergodicity breaking in problems like, for example, Fermi-Pasta-Ulam chain, and also in this and in a different context for spin glasses. So I guess in one case it appears like a dynamical thing, and in the other case it's sort of maybe more static. So I mean, could you just share your thoughts on this? The issue of ergodicity breaking and kind of, is there any similarities between these two situations?
Well, the point that of course is clear is that in some cases the type of phenomena are really equilibrium. In some cases the type of phenomena are more dynamical. And indeed, one of the things that I was trying, for example, to slightly modify the system in such a way, adding external forces of various kinds, in such a way that one could understand the breaking of things in a dynamic way. Of course, Fermi-Pasta-Ulam, on the other side, is, if this was a question, the dynamic, my feeling is that in Fermi-Pasta-Ulam, what happens that you really do not have a breaking of ergodicity in infinite volume limit, but you have only a very slow approach to ergodicity, which means that if the things behaves as a power, approach to equilibrium goes to very slowly, this is something that may affect, cannot be seen in simulation. Also, the other thing that I have the feeling in Fermi-Pasta-Ulam, that you must be very careful in exchanging the infinite time with the infinite size limit. And because you may have it may be different, but of course, Fermi-Pasta-Ulam is certain something which we have to understand better.
Okay, so there is a question from YouTube, somebody called David Brown. So the question is, what is the current thinking about your 1991 paper? A few remarks on low-dimensional string theory.
A few remarks on
low-dimensional string theory.
Well, this paper was essentially, I mean, there was this idea of one-dimensional theory or string theory, and there was all the way that this was connected to quantum gravity. And therefore, that paper, if I remember correctly, was trying to use the knowledge that one has on quantum, one-dimensional quantum gravity. One-dimensional quantum gravity was connected to the matrix model on which I worked in the 70s and the 80s, and therefore was trying to put together all the knowledge that can be gathered on this subject. Therefore, this was the aim of the paper. And after there was a similar paper in which we were looking the supersymmetric version that was done with Marinari and Zhang. So there was my incursion on quantum gravity, but at that moment I stopped because I have no idea how to go on in that direction.
Okay. Maybe the last question from Sanjay Jain. Sanjay?
Yes. Can you hear me?
Yeah.
Yes.
Professor Parisi, that was a very illuminating talk about your journey in physics. A question that I have is that some of the most outstanding problems in complex systems today are in the fields of biology and the social sciences. And it would be nice to have a perspective from you as to what you think theoretical physics and methods developed here, where they can contribute. What do you think is the is the role of physics in understanding complex systems of that kind, where real questions of evolution and organization, information, dynamics, etc., are involved?
Well, I think that there's a lot of works that have been done to understanding the evolution. For example, a lot of work that have been done, for example, by Derrida in this recent year, and there is a paper by Beaver and others for ecosystem and so on. And I think that there's I think that one has also to understand something that is important in evolution that sometimes is not present in simplified model, the possibility of some extinction. I mean, it's clear that we have to take care that the number of living species, the number of individual or living species is not infinite. Therefore, the fact that if the number becomes too small, the species become extinct is something that is difficult to characterize sometimes theoretically. So I think that there's a lot of work to be done, and it's not clear to me which will be the things that will be most relevant in the future, because often this kind of prediction are very difficult to be done, and therefore I refrain from predicting the future.
Okay, thank you very much.
So there is a last question here from an undergraduate. I'll read it to you, and you decide whether you want to answer this.
Yes, yes.
So you please explain the importance of classical chaos and nonlinear dynamics for our everyday life. Can you give examples?
Okay. So I think that most of the things that we see is most of the things that we see around is non-linear, and just a boiling of water in the kitchen is a quite non-linear phenomena. And the fact that you form some bubble that goes from below above in some region and not in some region, the way that it boils is a chaotic way, is non-linear, and has all these type of things behavior. So what happens, the things that would be more difficult would be to find the application in real life that are linear and non-chaotic, because nearly everything is of course, if well, there are some applications, things that are non-chaotic, but I mean, most of the interesting stuff is non-linear.
We are getting more questions, so I'll ask you. I mean, you've been talking for like about 2 hours, so.
No, I mean, I can answer. I mean, but I don't. You have to take a coffee break, so it's up to you.
No, it's fine with us. So I mean, as long as you are willing to take more questions, there are more people who are asking questions. So then I'll ask Bibi or Tata. Please unmute and ask questions.
Hello. Yeah. Am I audible?
Yeah.
Yeah. This is regarding because you might have done a lot of theoretical predictions, either by due to the existing experiments at that moment of time, or you might have predicted some theoretical done through your theory. Are there any experiments are yet to be verified of your predictions?
Well, for example, there have been. Well, I would say that, for example, there's a very nice experiment. There's one experiment that was done about 2000, 2001, about the fluctuation dissipation relation. And that was a quite impressive one in spin glasses. There's all the paper things that have been done on random laser that was done by the group in Rome that has also very good result. And the result that are done on really granular or colloidal system. And of course, there is one thing that I regret, that the experiment that was done on fluctuation dissipation relations on spin glasses was done 20 years ago, and I think that this could be done with much more precision this time, because I think that experimental techniques are much more precise, and also we get a very understanding from microscopic theory what happens. So I think that that was something experiment that I really would love to have done to test more precisely the theory. I mean, it's similar to the one that was done by Horsio and others, but it should be done with I think there's experimental technique are faster and that different, and that you can also computerize a lot of data taking that was done by hand or changing the type of system.
So in this context, may I just ask this question of whether your replica symmetry breaking scheme actually applies in 3 dimensions or not? This question is still being debated. I mean, do you have any?
Look, what happens if you want to ask? Look, the point is the following: what you mean by 3-dimensional system, in the sense that if you take a 3-dimensional real object, they have been produced, thermalized 1 day ago. I mean, they are recent object. Now, in 1 day, the typical time that you can afford in experiment, because you want to say under controlled situation, you can thermalize system up to 1 million. Not spin and 1 million spin. If you want to go to 10 to the to 1,000 billion spin, you should take the time of the universe. If you want to take to go to 10 to the 22 spin, you take in time that is really unthinkable on. Therefore, what we can say that the behavior of this system is in agreement on the predictions that one can do, and also the numerical simulations that we can do. Typical, I mean, long numerical simulation in which you can arrive up to 1 second can be done up on systems which are average up to 1 million spin. And the question, what happens for 1 million and 1 billion spin is something that is difficult, but this is, I think that is not the point, as was stressed also by Anderson. The point is the following: if the theory is going to, I mean, for example, it's quite evident that that in reality, persistent, for example, in 2 dimensions, there is no ferromagnetism. But if you have to describe a lower in 2 dimensions, a low temperature, ferromagnetism, or Heisenberg type, I meant, no Heisenberg ferromagnetism. But of course, if you have to describe a ferromagnet in 2 dimensions, you can see that up to a critical length that may be also 10 to the 14 in some case, mean field theory, we suppose in having spontaneous breaking of rotation symmetry described and asymptotically fades out. So it's quite possible, and that is something to understand, that replica symmetry is working well for system which has some size of the 1,000 of spin or maybe 1,000,000 spin, and when the system becomes very, very large, the things fade away and we don't have any glass transition and so on. But I mean, this does not mean that in the case where the experiment can be done, where the simulation can be done, it works. The point is just to extrapolate to infinite volume system. The point, the point for which spin glass simulations or experiments are so difficult is that if you take a ferromagnet and you pull a ferromagnet, the coherence length diverge when the time goes to infinity, like the square root of the time. So it's clear that this is very, very fast because you can take time of 10 to the 12 and you get a really macroscopic coherence length. Therefore, it's no doubt that you can really go to a thermalized very large system. When you go in the spin glasses, on spin glass experimental and numerical and so on, you have all the information that the correlation lengths and which, the regions that really thermalize, it goes like the time to the power 1/10, 0.1. Time to the power 0.1, it never becomes too large. Also, if you have some prefactor and so on. So this means that the extrapolation to infinite time of this kind of behavior is something that is difficult, and this gives some uncertainty if what happens to infinite time. But I would say that in the region of time that you can observe, in the region of size that you can measure, can you simulate in 3 dimensions a zero magnetic field, it is quite clear that the result is in very good agreement with the theory. If the point what happens in magnetic field, if a magnetic field that there is a transition that is disappearing in 3 dimensions, that is more complex things. There is a possibility that the upper critical dimension is 4 and not 3, but these are all things of details for which unfortunately we don't have a guiding system, because we have not been able for many technical reasons to do some kind of careful, let's say, renormalization group for this type of system. So we are missing the Wilson epsilon expansion for this system, and therefore we do not have every clear things. And of course, there is the argument.
Almeida-Thallos line that you're talking about, because there is Almeida-Thallos line, 80 line.
Yes, the Almeida-Thallos line is likely to be in a very high dimension, but the point is computing the point that around the Almeida-Thallos, there's a problem that the all Wilson expansion does not work, and not only because it's unstable fixed point. It's all the discussions of what happened there. We are working nowadays on seeing near the Almeida-Thallos, doing a simulation near the Almeida-Thallos and see what happens, at least in 4-dimensional things and so on. But it's clear that this is also a problem for which there could not be for the Lermeda-Taurus line a fixed manuseption expansion, because it was quite clear that cannot be done. We are trying to understand if we can understand these things at zero temperature. We are trying to do a 8 manuseption expansion for the Lermeda-Taurus, but all these type of things is incredible, much complex than what happens for ferromagnets.
Okay, yeah, thanks a lot for such a comprehensive answer. There's one more question. Can we just ask Mr. Adil Aman to ask a question?
Hello.
Yes.
Sir. Hello. Yeah. I'm good morning, sir. I'm an undergraduate. So I have one small question. So right now we see that the computational power has increased a lot as compared to in the last 2-3 decades. But in the 1980s, the computational power was much low. So if you are given the computational power of now, would you have done your research in a different way, like in a different approach? And if it is so, how different would it have been?
Well, the point is that the point was that first of all that we were trying to use the maximum computation power of the moment, and I think that the point was that there was some point of principle to understand the theory was did not need a large computation power to be produced. There were crucial, some Monte Carlo simulation were crucial on the energy of the magnetic property, but this was a very small amount of computation power. And I think that well, maybe if I had the computation time of nowadays at that time, probably I should have spent much less time to do simulations, but sometimes this is maybe not useful, for example, because one tool, for example, that is parallel tempering, gains as computer time a factor which is incredible, maybe 1 million and so on. So there was the point that we had to construct these new tools like parallel tempering just because we did not have enough computation time, and now we gain because we have a bigger computation time in parallel tempering. But having not enough tool in some cases is good because you have to substitute ideas. But for example, let me take lattice case theory. Lattice case theory is something that I've not been working on from the 90s on lattice case theory. But lattice case theory, again, from 90s, a factor maybe 1 million and so on from computing power. But again, also another factor, 1 million for better algorithm. The algorithms that are nowadays for, if one had to do with the computer power nowadays would be completely useless without the good algorithm. So in all this type of problem, the two things have to go together, improve the algorithm and improve computer power.
Mm-hmm.
Okay, so it's already been more than 2 hours. Giorgio, so thank you so much for spending so much time.
Thank you. You have been very kind.
No. So I mean, we really appreciate that you have taken so much time to spend with us.
It was a real pleasure. Thank you.
Thank you so much.
Thank you.
Thank you. Goodbye.
Goodbye.
Bye-bye.
Thank you. Bye-bye.
Bye-bye.
Bye-bye.